Welcome. This is the first in a series of video lectures on the principles of model predictive control, MPC. The objective of the series are first to understand the basic concepts of MPC. Secondly, to be able to engineer simple MPC applications. This first video will cover the understanding of the basic concepts of MPC, and in subsequent videos we will cover the engineering of simple MPC applications. Please note that this series is intended to be a practical lecture series, and it's not intended to delve into the theoretical issues, nor does it cover the detailed maths of how the MPC problem is solved. Let's jump into the deep end. We can say that MPC is a multivariable control algorithm that uses an internal dynamic model of the process and an optimization cost function J to calculate the control moves. Now, what does all this mean? We will use two examples. The first example is a shower model. The second example would be the speed control example to explain these points. This is Charlie taking a shower. This is an application of a multivariable control application. It's multivariable because Charlie simultaneously uses both the hot water tap and the cold water tap to simultaneously control the total flow and the temperature of the water coming out of the shower head. Let's say Charlie wants to keep the total flow constant, and we write a 0 there to indicate he wants to keep that constant, and he wants to increase the temperature. We make a plus there to indicate he wants to increase the temperature. He will do that by changing the hot water valve and the cold water valve simultaneously. So he will increase a hot water valve and decrease a cold water valve to give the desired response of a constant total flow and increase in temperature. Now, how does Charlie know how to do that? Well, part of that is he knows the response of the process. Let's write the response down. We can say the effect of changing the hot water valve and the cold water valve the effect of that on both the total flow and the temperature. So temperature. So if it increases the hot water valve, the total flow would increase. Increasing the hot water valve would also increase the temperature. Increasing the cold water valve would increase the total flow, but increasing the cold water valve would decrease the temperature. And this relationship there is called the internal dynamic model of the process. Let's just introduce some terminology. We have the total flow and the temperature, and we call those the control variables, CVs. Those are the variables that you want to keep at a required value. And then we have the cold water tap and the hot water tap, and we call those the manipulated variables. Those are the handles that you have to change to control your control variables. Let's just go back to a previous slide to check our progress. we previously said that MPC is a multivariable control algorithm, and we have demonstrated the nature of the multivariable control problem with the shower model. And we also said that it uses an internal dynamic model of the process. We also demonstrated that with the shower model. And now we will move on to the optimization cost function J. Now consider the example of speed control in two different scenarios to explain the concept of the optimization cost function J. The left-hand side, we have an ambulance with an injured person wanting to get to the hospital as soon as possible. The right-hand side, you have a family going on holiday, having misjudged the distance to the next fuel station. They run the risk to run out of fuel. The left-hand side, the control objective is to have very tight speed control. On the right-hand side, the ultimate objective of not running out of fuel translates into a control objective of minimizing changes in the accelerator pedal. This demonstrates an important concept in feedback control. You very typically have a conflict between accuracy and the cost of control, or fast changes in the manipulated variable. In this case, a manipulated variable is the accelerator panel. And the model predictive controller uses an optimization cost function J to resolve this conflict. Optimization cost function J equals to a CV weight, that's an adjustable coefficient, times the error squared, and the error is a difference between the required and the actual speed. And then we have a second term which is equal to a move suppression factor multiplied by the delta mv squared. And the model predictive controller will calculate control moves that will minimize the optimization cost function J. In other words, minimize the sum of the terms associated with minimizing the difference between the CV and the required CV, and minimizes changes in the manipulated variables. And then you have the adjustment that you can make. You can assign a value for the CV weight. You can assign a different value for the move suppression. And the values that you assign for the CV weight and move suppression respectively would be consistent with the specific control objective. So if the control objective is consistent with the application that we have there, where you care about tight control, so you care about minimizing the error squared, you would assign a high value for the CV weight and a low value for the move suppression factor. On the other hand, if the objective is more similar to this case, where you want to minimize the changes in the accelerator pedal, you would assign a high value for the move suppression factor and a low value for the CV weight. And many other cases, the control objective would be somewhere in between the two extremes as shown there, and then you would assign values that would reflect the relative importance of keeping the error small as opposed to keeping the delta mv small. And in each case, the model predictive controller would calculate the control moves minimizing J, and that would reflect the optimum solution for that specific scenario. Let's measure the progress. We use a shower model to cover the point of MPC being a multivariable control algorithm that uses an internal dynamic model of the process, and then we used the car speed control model to cover the optimization cost function J. This concludes the first video in the series. Looking forward to see you again in subsequent videos.